All right, so today we're going to talk about section 8.7, which is a topic called L'Hopital's rule. Little history for you here. This was credited to a guy named L'Hopital, who was a French mathematician, but he was actually studied calculus under Johann Bernoulli, and Bernoulli actually is the one who came up with these rules that we're going to learn today, but unfortunately L'Hopital took the credit for it. So here's a little picture of Bernoulli. We're going to switch gears a little bit from what we've been doing and talk about limits. And I want you to take a look at this limit here. So we have the limit as x approaches 2 of x squared minus 4 over x minus 2. And you remember with limits, we always look to see if we can do direct substitution first. So if we do direct substitution in this case, you'll see that we get 0 over 0. So when we do direct substitution on a limit like this and we get this expression 0 over 0, we call that an indeterminate form. Last year in Calc AB, of course, this was an easy one to figure out because we would just go ahead and factor the numerator, and you see the x minus 2 divide out. We get the limit of this expression, which is just 4. And as you'll recall in the graph, that 0 over 0 at x equals 2 gave you a whole. So what L'Hopital figured out was that there's another way we can evaluate this that might be slightly easier. And that is that if we take this expression and actually take the derivative of the numerator and the derivative of the denominator, and then evaluate that limit as x approaches 2, you'll notice we get the limit of 2x on top over 1. Now we can use direct substitution and we simply get 4. This is L'Hopital's rule. As long as that limit starts out as indeterminate, then we can evaluate it by taking the limit of the expression of the derivative of the numerator over the derivative of the denominator. The reason we didn't talk a lot about this last year when we were learning limits is because you didn't know derivatives at that point. But now you certainly know derivatives, so this might make it a little easier to figure out some of these limits. All right, so let's look at another example. We have the limit as x approaches 0 of 1 minus cosine x over x plus x squared. Observe for a second that if you were to just try and use direct substitution here, you would just have 0 over 0. So L'Hopital's rule says we're going to take the derivative of each of those expressions. Now we're looking at the limit as x goes to 0 of sine x on top over 1 plus 2x on the bottom. Now think about if you try to use direct substitution, what will you end up with? You'll have 0 on top and 1 on the bottom. So what is 0 divided by 1? The limit is 0. Keep in mind that 0 over 1 is not indeterminate. 0 over 1 is a number, that's 0, so that's why we stopped. Had we kept going with something that's not indeterminate, we would have gotten the wrong answer. Take a look. Suppose we took the derivative again, we would have gotten this expression, and then if we tried to use direct substitution here, we would have gotten 1/2, which is certainly not the limit. So the rule here is to make sure once you get to a point where it's not indeterminate, stop. On the other hand, you can apply L'Hopital's rule as many times as necessary as long as you're still looking at an indeterminate form. Take a look. We have the limit as x approaches 0 of this crazy expression over x squared. Observe that if you put in 0 for x, in the numerator you'll have 0, and in the denominator you'll have 0. So we have 0 over 0, so we're going to apply L'Hopital's rule. If you take the derivative of the numerator, next step, they just rewrote it here. Now take the derivative of the numerator, take the derivative of the denominator, and notice, again, if you try to use direct substitution, you would get 0 over 0. Check that for yourself and make sure you see it. So we can apply L'Hopital's rule again, and we get this expression. Now this time, if you substitute 0 in for x, you get a negative 1/4 on top, and a 2 on the bottom. Of course, that's not indeterminate, that's negative 1/8. So that's our limit. There are several other indeterminate forms that we're going to come up with. 0 over 0 is maybe one of the most common ones, especially one that you saw last year, but there's a few others that we need to consider. Another one that comes up a lot is infinity over infinity. Another one that comes up a lot is infinity times 0, which is not 0, by the way. Infinity minus infinity. Again, that is not 0, that's an indeterminate form, and we'll talk about how to handle these in a minute. 1 to the infinity is not 1, that's indeterminate. 0 to the 0 is considered indeterminate, and infinity to the 0 is considered indeterminate. So if you have infinity over infinity, this can be evaluated exactly like we did for the 0 over 0 terms. But for any of the others, before you can apply L'Hopital's rule, you must change the expression to a fraction first. So let's talk about that. So here we have the limit as x approaches infinity of x times sine of 1 over x. Think about if you tried to use direct substitution here. You would have infinity for the first term, and then 1 over infinity, of course, is really like sine of 0, so then you have infinity times 0. Since that's one of our indeterminate forms, we're going to rewrite this as a fraction so we can use L'Hopital's rule. Let's see what I did here. I took this x that was on top, and I moved it to the denominator by making it 1 over x. A little algebra trick. You see those are the same. Now if you try to use direct substitution, you get sine of 0 on top, over 0, which is still 0 over 0. I haven't applied L'Hopital's rule yet, all I've done is rewritten it. So I should still get an indeterminate form, which I do. But now it's in a form where I can apply L'Hopital's rule. A little aside here, you could have evaluated this using this rule if you remember from Calc AB last year. The limit as x approaches 0 of sine x over x was 1. As long as these two expressions were the same, that was always 1. But if you didn't think about it, we could just use L'Hopital's rule. Take the derivative of the numerator. So we have cosine of 1 over x times negative 1 over x squared. Notice the chain rule there. And then the denominator, of course, the derivative is negative 1 over x squared. So what happens to these two expressions? We divide out. So we're just looking at the limit of cosine of 1 over x as x goes to infinity. And remember, 1 over x, of course, goes to 0. Cosine of 0 is this one. Okay, let's look at another example. So we have limit as x approaches 1 of 1 over natural log of x minus 1 over x minus 1. Notice if we put in 1, the denominator, natural log of 1 is 0. So 1 over something going to 0, back to last year, the denominator gets smaller, the fraction gets bigger, and goes to infinity. Same thing with the second expression, equivalent to infinity minus infinity, which remember was one of our indeterminate forms. We're going to get this into a common denominator so we can get this into a fraction. If I just get a common denominator, I've got this expression. Of course, this is still indeterminate. We get 0 over 0. Haven't applied L'Hopital's rule yet, so we're going to apply it now. The derivative of the numerator is this. The derivative of the denominator, if I do a little product rule here, is this. In the next step here, I cleared the fractions. This isn't entirely necessary, but I went ahead and multiplied everything through by x just to make it a little cleaner fraction. Notice if I plug in 1 this time, I get 0 over 0. Of course, that's indeterminate. So we're going to apply L'Hopital's rule again. Derivative of the numerator, of course, is 1. Derivative of the denominator is 1 plus natural log of x. Little product rule here. So now if we plug in 1, Natural log of 1, of course, is 0, so this just leaves us with 1/2. All right, let's look at some that are in the indeterminate form, 1 to infinity, 0 to the 0, or infinity to the 0 power. So we're going to look at these, and we're going to use a little mathematical trick or algebra trick here to change this into a fraction. Recall from pre-calc, of course, the natural log of u to the n, log property, you can bring n to the front of that log. And notice also that if I wanted to, I could write that expression like this. We saw that in an earlier example. To make that n go to the denominator, we write it as 1 over n. Notice that's a fraction, which is what we're looking for when we work with L'Hopital's rule. Another trick you're going to see that comes up in the next example. Take a look at what I did here. If I have the limit of f of x as x approaches a, notice that I could rewrite that as e to the natural log of that limit. The e and the natural log are inverse functions. You see these are the same expression. Now, why am I doing that? Probably because I'm going to bring in, if I introduce this natural log, I can use this exponent to the front. You'll see in a second. We're going to do an example. I want to also point out that there was a property with logs that said, property with limits that said this natural log could be moved inside the limit. So notice from this step, I just took this natural log and moved it into the limit here. How does this help us? Let's look at an example. So we have the limit as x approaches infinity of x to the 1 over x. Make sure you see that this is indeterminate because this would be the form infinity to the 1 over really large numbers, which is 0. So that's infinity to the 0 power. What I'm going to do is I'm going to do that little algebra trick I showed you on the last slide, and I'm going to rewrite this as e to the natural log of this limit. Now that I have that natural log in there, I'm going to pull it through the limit. And now think about, here I've got this natural log, and I have this exponent of 1 over x. So what can I do with that 1 over x? Bring it to the front of that log. Now you'll notice, what do I have here? I have the natural log of x over x, which is a fraction. If I take the limit of that, so I'm just ignoring the e for a second. If I take the limit of this expression as x goes to infinity, we have infinity over infinity. Think about the log function. As x goes to infinity, it just keeps growing. That's indeterminate, so we're going to apply L'Hopital's rule. Again, I'm ignoring the e. I'm only looking at this limit. We have 1 over x on top over 1. So now as x approaches infinity, 1 over x will go to 0. So what am I left with? E to that limit, which just goes to 0. The final answer is